Okay, our next speaker is Katie Crotts from STScI to talk about the wild structure of Beta Pictoris in MIRI imaging.
Yes. Can you all hear me okay? Okay, great. All right, hi everyone. I'm very excited to be here today and to show you some really cool new observations of the Beta Pic disk with MIRI. Okay, perfect. I just also want to emphasize that while I'm giving this talk, this is very much a group effort. So I've highlighted my collaborators in the lower right here, a lot of whom are here today and are giving talks as well, or have given talks. All right, so I'm just going to fly through this slide since we kind of got a good introductory talk already from Christine, but I just kind of want to emphasize that the disks that we are directly imaging are these kind of cold Kuiper belt analogs, and we believe that the planets in the outer solar systems in these systems could be directly sculpting these disks and creating all these wide range of morphologies. I will note, though, in most cases, as we kind of talked about earlier, we have not found many planets in most of these debris disk systems. However, we do have one system that has a known planet and disk, and that is, of course, Beta Pictoris, which is one of the most well-studied and famous debris disks to date. So as Paul mentioned earlier, this disk was first imaged back in the 80s. And since then, we've been continually learning more about this system and its interaction with its planets. So for example, in the late 90s, early 2000s, it was seen with HST that there is this kind of warp component to the disk, and it was predicted that this warp could be caused by a planet on an inclined orbit. And this was later confirmed almost a decade later with the detection of Beta Pic B. All right, and since then, this disk has been imaged with just about every high contrast imaging there is, and on multiple different scales. So we can see kind of the outer solar system, outer system, as well as closer in where we see this warp. And so I want to also focus on these ALMA data. As we see that there appears to be this clump of dust and gas on the right side of the disk, and this has been predicted to be potentially a recent massive collision in the disk. So this leads to the discovery of the cat's tail in 2024. So you can see here, we have this extended feature, and it's hypothesized that this cat's tail is caused by basically a distribution in the dust grain sizes where you have dust sizes that are being blown out of the system and kind of creating this tail. I also want to emphasize that we don't see this feature in scattered light. And it's hypothesized that this could be because the material making up the cat's tail is this kind of dark organic material that we could only see at MIRI wavelengths. All right, so this brings me to our new data. So these observations were with the coronagraphic mode of MIRI. Our new observations is with the direct imaging mode. So we're able to get a wider field of view and see if some fainter features. So here we go. This is our new observations. Yes, feel free to ooh and ah. So as you can see, again, we're probing the disk at much farther distances than the original MIRI observations. And we're seeing all these interesting new structures, like what is going on out here? I also want to shout out to Miles Curry and Callum Lawson, who worked on the reduction for this data. And I also want to emphasize that this image here is a combination of 15 micron and 25 microns. All right, so let's kind of dive into what we're seeing here. So we can still see the cat's tail. very clearly in the bottom right there. But then we're also seeing a bunch of new substructures. So on the left here, we have the warp component that kind of comes down, but then it weirdly comes back up and crosses the main disk component. So very interesting. It also has a couple of wavy features. And then additionally, we have kind of this curlicue structure that we are lovingly referring to as the pig's tail. And then we have these parallel planes of material that may seem to be possibly connected to the pig's tail as well. So what is going on here? What is happening? Because we have not seen features like this in other debris disk systems. So we have some evidence that suggests what could be happening. First of all, if we look at the color of this combined image, we see that the main disk component is more red, and then all this other material, there you go, including the cat's tail, this nebulous material, and the warp feature is more blue than the main disk. So that suggests that there's probably some difference in the dust grain properties between these two components. And then also, when we look at the pig's tail and these parallel planes of material, oops, go back. It almost seems like there's some episodic event going on, like dust is being continually blown out of the system. So kind of based on these evidence, I made a little diagram here kind of showing what our running hypothesis is. So you have the planets in the system, Beta Pic B and C, that's creating this warp component in the disk. And then at some later time, you have this later collision, and which creates the cat's tail based on the dust grain size distribution. And then as the planet is orbiting around, that's going to cause this material to become coplanar with the planet's orbit. And then over time, you have this episodic dust events. And whether this is because Beta Pic B is interacting with this material, or it's just collisional, or continuous collisions in the disk is not well understood yet. All right, so this is kind of where I come in. This is my contribution to this project, running some n-body simulations to see if we can potentially explain some of these structures. So just as a starting point, having the planet Beta Pic B, I did add C in there, but it caused my kernel to crash. So we're starting with Beta Pic B for now. And then adding a disk of massless particles representing the disk, having that run for some time to establish kind of the warp structure. And then at some later time in the simulation, adding a bunch of extra particles that represent the collision in the disk, and that creates kind of these particles will have a particular orbit based on the physics of the collision, which usually creates kind of this tail on the left side and then a pinch point on the right side. So having run this for several hundred to several million years, this is the starting results, I should say. So have not yet been able to get all the features in the disk, but we can at least kind of explain one thing so far. Like, again, this is very preliminary. So because the collisional particles have this kind of tail on the left side, and then you have Beta Pic B, which is causing the dust grains closer in to become warped as well, we create kind of this geometrical effect where it looks like the warp on the left side is warping back up towards the main disk midplane. So it doesn't quite match 100%. We still are not getting all like the wavy features in the disk, and obviously we haven't gotten any of this pig's tail or the parallel planes of material yet. That's going to be more modeling down the road, adding some unbound particles into the system. but it's a good starting point for now, and it shows that with the planet and collisional material, we can at least somewhat explain what could be going on in the disk. All right, and then to end things off, we also got some MRS data of the cat's tail specifically. Shout out to Keelan Hoke, who actually worked on this data and sent me these figures. So on the left here, showing the data, and what Keelan did here was take two apertures, place one of them on the cat's tail, and then place one of them on the main disk at a similar radius. And so these are the results. Haven't been able to define any particular features, absorption features in the disk. But what we can say based on these preliminary results is that the main disk in the blue here is colder than the cat's tail. And so this kind of is consistent with this theory that the cat's tail and probably all the other bluer material is made out of this dark refractory organic composition. So you could kind of think of it as like dark sand versus white sand. When the sun beats down on it, the dark sand's going to become hotter and emit more. So that's kind of what we're seeing here as well. All right, so in conclusion, the Beta Pic disk continues to amaze us, and we continue to learn more about what's going on in this disk and changing our understanding of planet disk interactions and massive collisions. So our data kind of is consistent with a massive collision in the disk, and then that material is being interacted with the planet. And I'm just going to leave it here on this image here, showing kind of the comparison between the new MIRI data and scattered light data, just to kind of show the different scales. And I'll take questions. Thank you so much.
Gotta say, wow. The chair would like to ask 3 or 4 questions, but that's not fair. So I'll only ask, sort of one question. Is the temperature of those grains in the far out features, is that consistent with them being tiny grains blown out by radiation pressure?
Yeah, so yeah, the particles, at least based on my simulation work, the smaller particles are going to be blown out farther than the bound dust grains. Or I should say they're actually, in my simulation, they're all bound dust grains, but the bigger beta values, so smaller dust grains, are going to be at farther separations from the star.
Okay, I'll come back to you on that.
Yeah.
Okay, where are the audience questions?
So,
Clarissa, you've got one?
Very nice talk. Eric Gaitis, University of Hawaii. So one comment, one question. The comment is that you can also get differences in emissivity due to grain size differences.
Yes.
And so that is an alternative, not necessarily mutually exclusive to the composition of the cat's tail. The question is basically, have you thought about doing a second epoch? Because if these are moving at 100 kilometers per second away from the star, in a year or two, you should be able to clearly detect the motion of any sort of cross-correlation of the image to see if the structures are moving.
You'll have to ask Marshall about a second epoch.
This was the second epoch.
That's true, yeah.
But not in the same mode, right? So I mean, a second epoch of direct imaging. I mean, this is partly motivated by AU-MIC, which is a quite different system, but still a debris disk. We see structures that are actually moving in time.
Yes.
That are being blown out.
Yeah, so with AU-MIC, that's those clumps of dust are kind of driven by the stellar winds. That's probably not going on here in Beta Pic, just because it's an A star, so the stellar winds are probably not as strong. But yeah, I agree with everything you said. Definitely the grain size is going to be a factor in the disk color and temperature. The theory of it being a dark organic material is due to the fact that we don't see it in scattered light. And yeah, we have actually compared the location of the cat's tail with these observations compared to the previous observations, and there's like it's very tentative possibility of the cat's tail moving, but it's not clear if that's from like misalignment or distortion issues.
Okay, there's a question on the other side.
For these, you're hypothesizing that this dust, like these organic things, compounds. Are there analogs of that in our own solar system in like the Kuiper belt for these kind of things, or like are there other comparisons we can make to the solar system on this?
That's a really good question. Marshall, you look like you want to answer.
Specifically, the Liam-Greenberg-1997 refractory comet dust model. It's very similar to like OSIRIS-REx stuff that got brought back. So think like charcoal black asteroid comet stuff.
Is this stuff weathered on the exterior or deep in the interior? Exterior, okay.
You're the one that thinks that.
The one difference between what we've seen from asteroid sampling is that we need really high porosity. So the high porosity is what drives the temperature here, in addition to the blackness. It's not clear that you can form flash dust bunnies after a collision, that they can stay together, whether they're condensing again after a collision. We don't know what's going on.
Okay, well, we're formally out of time. Sorry, but let's make sure to come up and talk to Katie about this great results. Thank you.